All right. Yeah, on Monday, when I was gone, I'd asked you guys to read about the double angle identities and power reducing identities. So the double angle identities are these three. The only one that's a little bit tricky to deal with is the cosine one, because there's three different versions that you can kind of choose from. They're all equivalent, and you can kind of make any of them work, but obviously if you choose one version over another in like a proof problem, it could make your life much easier doing it or choosing one versus another. So you have to be a little bit careful and try to think ahead a little bit. So these are the three double angle identities. If I were to try to derive one of these identities, what do you think I would do to do that? Ben? So let's say I wanted to like prove or derive the sine of 2u. Well, what I'm going to do is I'm going to use the identities that we just developed last time. So I'm going to think of 2u as u plus u. And now I can use my angle sum identities that we developed the last time we met. So if I do that, I would get sine u times cosine u plus cosine u times sine u. And because multiplication is commutative, it doesn't matter the order in which I write those two things. They're like the same term. So I would just add them together and have 2 sine u cosine u. Okay with that idea? And I could do a similar thing to get the other two identities using the same angle sum formulas that I had from the previous. Okay with that idea? And that's a nice, clever trick that we can always rewrite, like 2x as x plus x, or 5x as 2x plus 3x, or however you want to kind of break it up to be able to use your identities. But that's a nice little trick, and that's what we would do to kind of get the other ones. That's okay. Everybody okay with that idea? You see the little sneakery that we pulled there? In 6.2, we look at the power reducing identities. So these are the three power reducing identities, and what they are going to do is it allows me to rewrite a power of a trig function without the exponent. But in doing so, I create a double angle. How do you suppose if I wanted to derive like sine squared equals 1 minus cosine 2u over 2. How would I get that one? The first one. It's quite easy, it turns out. Let's go back and look at my double angle formulas, specifically this one. What's the power reducing model, or the power reducing identity for sine squared? It's this double angle formula just rearranged, right? All I did was get the sine squared by itself, and it's now the same thing as the power reducing. Is everybody okay with that? We can see that? Shouldn't be hard to see that, right? Okay. So let's do a quick example where we're going to just find the exact value of this trig function using a power reducing identity. So let's say we want to find sine squared of 3 pi over 8. Now notice here that 3 pi over 8 is not a unit circle value, so you can't compute this directly. Now, if I apply my power reducing model though, how would I rewrite this, or the power reducing identity? If I look above, it's 1 minus cosine of 2u all over 2. Everybody's okay with that? What do I get when I multiply 2 to the fraction 3 pi over 8? Should be able to do that in your head. Should be quick, should be easy. 11 pi over 8, we're not adding here, sir. That's being multiplied. I would get
6 pi.
How about 3 pi over 4 as the best answer? That's the same thing, right? But it's simplified. And why would reducing that fraction be really important? Because this is a unit circle angle. The other one was not written as a unit circle angle, right? 6 pi over 8, you could look on your unit circle for a long time. If you didn't think to reduce that, it's unlikely you'd notice it. 3 pi over 4, though, is a unit circle value, and you'd be unlikely to not see that. So if I go to my unit circle and retrieve the value for cosine of 3 pi over 4, I get negative root 2 over 2. Now, who likes the way this answer is written right now? No, what's wrong with it? Okay, you have the double negative. Sure, what else is wrong though? You have a fraction in a fraction, right? We typically don't want to leave that as a final answer. So what's the trick that I can do to kind of get rid of that fraction inside of a fraction? How about I multiply just by 2 over 2? So when I multiply 2 to the numerator, I do that, and then I also have to multiply the 2 in the denominator. So that gives me 2, and then minus a negative is a positive, and the 2 in the denominator cancels out when I multiply the 2 to it. We have 4 in the denominator. Everybody okay with that idea? what if we want to do cotangent squared of negative 165 degrees? Now, at first glance, you might not think we're able to do this because we don't have a power-reducing identity for cotangent, right? What can we do instead? Yeah, I can change this to tangent. So what is cotangent squared in terms of tangent? Yeah, 1 over tangent squared of negative 165 degrees. Good. And now I can apply my power-reducing model, or identity, excuse me. So I put the heavy fraction bar there to differentiate like that fraction bar, right? Just so nobody's confused on kind of what's the numerator and what's the denominator there. Okay. Now, who likes the way this is written? Pretty gross, right? What's the issue? I got fraction inside of a fraction, but this one's really easy to deal with. How do we deal with it? We just make the reciprocal, right? 1 over something is just making the reciprocal. Does that make sense to everybody what I did there? Like 1 over a half is just 2 over 1, so 1 over the fraction is just the reciprocal of the fraction, right? Seems the easiest way to deal with that. Okay, now what? What am I looking for in this problem? The exact value for this. So what do I do next? Okay, you could go to the unit circle and you could probably figure out where negative 310 is on your unit circle, right? But there's a little bit of an easier way here. We have an identity that can deal with a cosine of a negative angle, right? That's one of our odd-even identities. So it turns out that cosine of the negative angle doesn't matter. It's the same thing as the cosine of the positive angle. That just makes life a little bit easier because now we don't have to try to track backwards along the unit circle and do all that stuff. And then it would help if I multiplied 2 times 165 correctly, right? How come nobody's hollering at that? What should that be? 330. That is called an 8 a.m. mistake right there. That's the kind of mistake you make at 8 in the morning when you're trying to do math. Okay. And those are unit circle values, correctamundo. So that is root 3 over 2. Okay. Who likes the way this looks? No. What should we do to it? Yeah, let's multiply by 2 first. That'll get rid of the fraction inside of fraction stuff. And now already you might say, we don't like this as a final answer either, right? What's wrong with it? It's a square root in the denominator. So how are we going to take care of that? It sounds like JJ already had an idea there. Yeah, so what are we going to multiply to the top and bottom of this? Not square root of 3. 2 plus the square root of 3. Because now if I look in the denominator, what I have is that difference of 2 squares, which I think is what JJ was shooting for. So the numerator, I have to FOIL that out. Everybody's okay with that. In the denominator, I can just use the difference of 2 squares factoring pattern, where I know that's just going to be a squared minus b squared. So if we simplify things down, then in the numerator, I get, what, 7 plus 4 root 3. And in the denominator, I get, what, 4 minus 3. So that's just going to be 7 plus 4 root 3 as our final answer. Any questions on what we did there? So the pretty relatively easy question, right? We had to go back and call back some old algebra skills to make sure we didn't do anything goofy there, but it was all things that we hopefully at least look familiar and like, oh yeah, I kind of remember doing that. Might have needed the reminder, like you wouldn't have thought on it your own without having been reminded, but you should be able to do it once you're reminded, right? When I write here PRIs, what do you think I mean there? Power reducing identities, yeah. So that just me, that was a lot of words. Just wanting to kind of avoid that. So which side do you think I should work for work my proof with? I would do the left. Why would I use the left? Because if the instructions say to use power reducing identities, I don't see any powers on the right hand side, right? So if I'm supposed to be using the power reducing identities, I want to start on the side where there's a power. Everybody is okay with that idea? Okay. Notice the power reducing identities all require like a squared trig function. Right now I have a cube. What do I do? Yeah, we'll just write it as sine times sine squared. Everybody's happy with that? Then I can just use my power reducing identity on the sine squared. What do I get when I do that? One minus cosine 2x all over 2. And look what we got. That's it, right? What's dividing by 2 the same as? Multiplying by 1/2, right? So really what I have is just these 3 things being multiplied together, right? And can I write a multiplication problem in any order? Yeah, when I'm using real numbers, I sure can. So that's it. Not too bad. So those were all things that I'd asked you to kind of look at on your own on Monday when I was gone. Here I'm going to look, or today we're going to start talking about the half-angle identities. Oops. And here, it's the tangent that's kind of the pain in the tuchus, because we have 3 different versions to kind of work with. So, if I wanted to prove one of these identities, what am I going to use? If we're following a familiar pattern here. Let's say I wanted to prove this one. Or derive this one, let's say. Maybe that's a better word to use here. Well, what was the last identity we just talked about? The power-reducing identity. So I'm going to use the power-reducing identity on sine squared equals u over 2. So that's going to give me 1 minus cosine of 2 times u over 2 all over 2. Notice what's happening inside the cosine there. The times 2 and divides by 2 cancel. So I just have that. And then if I square root both sides, that's going to get rid of the sine or the squared, leave me with just the half angle for sine. And because I was the one taking the square root of both sides, I generate the plus or minus. And there's my half angle. So it's a direct consequence of the power-reducing identity. Notice the pattern here that we've used. We only did one geometric derivation here, right? We geometrically derived like sine of u minus v, right? You guys remember that? Or cosine of u minus v? I think it was cosine. And then from there, we just used the new other identity to prove the next ones, right? We haven't gone back to the unit circle or the xy plane to do any more of these derivations. We just used previous identities to build out the next ones, which is nice, right? That's the way we'd prefer to do it. Nobody wants to go back and like to the xy plane and try to do this geometrically. It's really kind of a pain to do it that way. but rather elegant to go and just use the previous identity. So let's use our half angle identity to find the exact value for, say, cosine of 75 degrees. So I need to rewrite cosine of 75 as cosine of something divided by 2. What should that something be? $150, right? 75 divided by 2 is 150. Everybody's okay with that? Now I'm going to apply the half angle formula. I think Vin Diesel just pulled up. That joke would have been funnier like 10 years ago. Everybody's okay there? Okay. So now we'll go to the unit circle and pull the value for cosine of 150. So if I do that, that is negative root 3 over 2. Now, do we like the way that this answer is written? No. What's the first thing that sticks out that's problematic for us? I would just worry about the fraction side of a fraction first, right? Everybody sees that? So what am I going to do to try to get rid of that fraction inside of a fraction? What am I going to multiply by? You say 2 over 2. That's not quite right. Yeah, I need to have the square root of 2 over 2. Why do I need the square root there? Yeah, because the other thing is under a square root. I mean, just recall that, say, like 2 times the square root of 2 is just 2 root 2, right? But the square root of 2 times the square root of 2 is the square root of 4, right? That's what we need to take advantage of. So these can then distribute in. So I'm going to give 2 minus square root 3 over 4. Everybody agree with that? And the square root of 4 we can deal with, right? What's the square root of 4? Just 2. Everybody's okay there? JJ? Sure. Okay. Now we have one more thing that we need to resolve, and it's the plus or minus. Should this answer be positive or negative? Which one? Why do you say positive? Nope. Since the angle 75 that we're evaluating the cosine of is in the first quadrant, using all silly turtles crawl, I know cosine needs to be positive in the first quadrant. So we're just going to have the positive one, and that is going to be our final answer. We're not going to be concerned with the fact that I have a square root inside of another square root. That's okay. NBD. Are we okay with that one? What do you guys think? Not bad? Not really any worse than the other ones, right? What if I wanted to do tan of negative 105? So I think that should be a B, though. So what am I going to rewrite this as? What am close? Negative 210. Still got to have that negative sign on there. Now we have some choice with the cotangent half angle identity, right? We have three options there. Which one of those three do you want to use? Does it really matter? No, doesn't matter which one you choose, but certainly some of them look a little easier to deal with than others, right? Which one would I choose? Or which one do you think we should choose to make it the easiest? Let's start there. I would pick 1 minus cosine x over sine x. Why would I choose that one? Because there's only one thing in the denominator. I have no square root to deal with. That makes life a little easier. And then I only have one thing in the denominator to deal with. That means I won't have to rationalize the denominator. If I have to do that, will be really easy. I won't have to multiply by a conjugate and have to do a difference of squares and any of that nonsense, right? It'll be kind of the easiest case scenario in this kind of a problem. That's the one that I would choose. Does that make sense why I'm choosing that one? Now, does it really matter which one I choose? No, but if I can make my life a little bit easier by making good decisions, that feels like a good idea to me. You know, my life is hard enough. I don't need to make it harder because I'm doing dumb things. Maybe not dumb things, maybe careless things or thoughtless things where I didn't put any thought into making it, can make my life easier here. Everybody's okay here? What do you want to do next? I'll tell you what I would do next is I would use my odd-even identities to get rid of the negatives. So cosine of a negative is the same thing as cosine of the positive. Sine of the negative, though, is negative sine of the positive. Now let's just go to our unit circle and find our values. So if I go to 210 degrees, cosine is negative root 3 over 2. And sine is negative 1/2. Everybody okay there? Who likes the way this looks right now? Barfaroni, right? What should we do to kind of get rid of these fractions inside of fractions? We'll just multiply the top and bottom by 2. So I got to make sure I multiply it to everything in the numerator and everything in the denominator. Oh, silly me. There's no negative sign there. Right? Who was about ready to ask me why that 1 was still negative? Shame on you if you were not. Just blindly copying everything I do down like I don't make any mistakes. You guys have been in this class long enough. You know that happens like multiple times a day. And you catch me at 8 o'clock in the morning and woof, you know, things get worse, right? All right. Let's say we want to prove 2 times cosine squared x over 2 secant squared, or I'm sorry, secant x equals secant plus 1. Well, which side do you want to work on first? The left side is probably the obvious one, right? What do you want to do first to the left-hand side? Get rid of that 2. Well, I see 3 2's in the left-hand side. I'm unsure of which one we're talking about. You talk about the coefficient, the squared, or the divided by 2. How are you going to get rid of it? I would do the half angle first. That's what I would do first. Typically, what you want to do first is to get the variables the same, so everything is like x's only. You're going to have 2x, or x over 2, or x plus y, or you want to get everything like a single variable inside, because then all of a sudden all the identities from our first page can kind of combine together in ways that make life easier. So if I go and I look at my identity for the half angle identity for cosine, I have plus or minus square root 1 plus cosine of x over 2. And now that's still going to be squared. Why is the square down there? Yeah. So that's where the squared is coming from. Everybody's okay with that? Now it's really nice that the squared is there. What's the squared going to do? Cancels the square root, sure. What else is it going to cancel? Not the 2. What was that, Miguel? The plus or minus. Why is it also going to cancel the plus or minus? If I square anything, what does it have to be? Positive, right? Everybody's okay with that? So now we're going to have 2 times 1 plus cosine x all over 2 times secant x. Everybody happy to hear? What do you want to do now? Yep. So Megan says let's cancel those 2's. So that's going to be 1 plus cosine times secant. Okay, that looks pretty good so far. Certainly we've gotten a lot simpler, right? What do you want to do next? I would do this. Because look at where we're trying to get to. And why is that a great thing? Secant is just 1 over cosine. So there's my 1. You thought I got rid of it by distributing through. What do you guys think? Not terrible, right? Okay. So in 6.4, we're going to talk about proofs and solving. There's no new identities here, but now all of a sudden we have the option to use any and all of the identities we've talked about to do some of these proving and solving problems. So let's say we wanted to prove 2 cotangent of 2 alpha is equal to cotangent alpha minus tangent alpha. Which side would you work on here? I would work on the left side. Why would I work on the left side here? Yeah, because I have that double angle going on there that I know I have an identity right away that I can use on that. But here's the thing. Do I have a double angle identity for cotangent? No. So what am I going to have to do? Yeah, I'm going to have to turn it into a tangent. And then I can use my double angle formula for tangent, right? I'll draw that heavy division bar, just so everybody's clear at what's where things are now. We good with that? Okay. Let's get rid of this fraction inside of a fraction. So because it's just 1 over a fraction, it basically just means to write the reciprocal. And then what do you notice we can do here? Yeah, that's what I would do. Cross out those 2's. And then what's the trick here? There's something tricky I'm about to do algebra-wise. Yeah, kind of. So I'm going to write this fraction that has a common denominator as the difference of 2 fractions. Everybody okay with what I did there? Now note that this trick that I'm doing only works if you have like a single thing in the denominator, right? You can't break a denominator up into like the sum or difference of 2 different fractions like we did there. The denominator has to be the same in both fractions when we break that apart. Okay, what do you notice? That was the tricky part. Okay, and then what about the other fraction? Yeah, that cancels down, and we're left with cotangent minus tangent, as required. Okay, what if we wanted to do cosine 4x equals 1 minus 8 sine squared x cosine squared x? Which side would you work on? I'd work on the left. I find that it's usually easier to go from coefficients to no coefficients. But we don't have a 4x formula, right? Only 2x. So how do you want to think about this then? Yeah, that's exactly what I would do, Miguel. So I'm going to think about it as cosine of 2 times 2x. The problem, though, is how many double angle formulas do I have for cosine? 3. Which one of those 3 do you want to choose? Look carefully at what we have left. And let's make a decision here, because you can do something that makes your life really difficult or something that makes life much easier, but we got to be a little bit careful there. Good. So Megan says 1 minus 2 sine squared is the one that she would use. Why did you pick that one, Megan? Yeah. So because this one started with 1 minus, let's pick the identity that also starts 1 minus. That seems like a solid bit of reasoning. Now notice here that I'm getting, when I apply this identity, I don't get 1 minus 2 sine squared x. I get 1 minus 2 sine squared 2x. Why is the 2x there? Because that was the u basically in our double angle, right? Does everybody see that? Okay, what do you want to do now? Well, I see another double angle to do, right? Don't you guys? So let's do that. I guess I can move that highlighted. I don't know why I was wanting to erase it. So the double angle identity for sine is 2 sine x times cosine x. And because we had sine squared 2x, we have that double angle identity squared. How do I square something like 2 sine x cosine x? Because everything is being multiplied, that squared applies to everything, right? If those things were being added or subtracted, what would you have to do? FOIL, right? Everybody okay there? And it is now all coming together. We can see the finish line, and there it is. We've nosed across it. Okay, so solving. These new identities that we have now are extremely helpful in solving problems. Because remember how big of a pain in the butt it was to solve those double angle and half angle solving problems that we had before? These identities provide us a way to kind of get around having to deal with that. So they are extremely nice. So let's look at this one here. Let's solve cosine 2x equals sine x. What should I do first? Let's do a double angle. Okay, which of the 3 double angle formulas for cosine do you want to use? Okay? There's really one that should jump out at you. And for good reason. You'd really want to be using the third one. Why do I want to use only the third one and not the other ones? Yeah, because now we have only one type of trig function. We just have sine x's. If you're solving, if I can get things so there's only one type of trig function, that's best, right? Sometimes that's not possible, and it's okay if everything is multiplied together, because then we can still use the zero product property or whatever. But we got to get them down to a place where we have just one trig function in those things we're trying to solve. All right, now what? Let's get it all on one side. So I'll add over the sine squared and then subtract the 1 over. Now what do you want to do? Oh, guys. Factor! Abby, what's up? I moved this side over to that side, is what I did. But yeah, you could do it the other way, but then you have a negative in your leading coefficient. It's just usually easier to factor if there's not the negative there. So that's why I did it that way. But it's not wrong to put everything on the other side. It just doesn't really matter. So notice here, if I'm going to factor this, it's a little bit more difficult because the leading coefficient isn't 1. So I'm going to need to find the two numbers that multiply to give me a times c, and then add to give me b. What are those two numbers? 2 and negative 1, right? Shocking, they're the same two numbers I multiplied together. So what do I do with those two numbers is I rewrite sine x as 2 sine x or plus a negative 1 sine x. And then I make my two groups. From the first group, I can take out a 2 sine x. And that's going to leave me with sine x plus 1. And from the second group, I can take out a negative 1. That leaves me with sine x plus 1. And then if I look at the whole thing, I see that I have sine x plus 1 in common in both places. And when I factor that off, I'm left with 2 sine x minus 1. Everybody kind of remember that long factoring method from last year in your Algebra 3-4 class? Comes up often when we're solving these trig equations because, well, if sine or cosine is, bigger than 1 or less than negative 1, you can't find the inverse for it, like it doesn't have a solution to it. So oftentimes these problems have these coefficients so that you're stuck getting a solution. You know what I mean? It's not a very interesting problem if both of them are no solution when you make the two factors. All right, so we subtract 1 from both sides here, and then do the sine inverse of both sides. If I go to the unit circle, this is exactly 3 pi over 2. Same idea over here. I add 1 and divide by 2, and then I do the sine inverse of both sides. And I go to the unit circle and look up the places where sine is 1/2. So there are my solutions. Notice here I didn't have to mess around with like doing the double angle thing that we had to do last semester not last chapter. Was it last chapter? It was chapter. I don't remember when it was. Yeah, I think it was last chapter. Where I had to like look to see if there's any extra answers inside the unit circle or whatever. It was not that bad. Okay, what about this one? Sine 2x equals negative 2 cosine squared x, and we're solving on from negative 4 pi to negative 2 pi. What do you want to do first? Double angle? Okay. Now what? I would get it all on one side. So I'm just going to add the 2 cosine squared to both sides. Now what? Don't tell me to divide by cosine. Many of you did that on the last test, and that made my heart hurt. That's how you lose solutions when you do stuff like that. What should you do instead? Factor. So notice that each of these have a 2 cosine in it. Everybody's good there? So if I set these each equal to 0, that first one's easy, although those aren't the 2 answers that I actually need because they're not in the correct interval, but we'll deal with that in a minute. What about sine x plus cosine x? What am I going to do with that? I'm going to make a tangent. So the way I'm going to do that is I'll subtract cosine from both sides, and then I'm going to divide by cosine. Because that makes a tangent. So if you have a sine plus cosine or something like that, you can make a tangent out of it. That's a nice trick. And so when I do that, I get, go to the unit circle, that's 3 pi over 4 and 7 pi over 4. Now, none of these are the actual answer I want, right? Because none of these are actually on the interval from negative 4 pi to negative 2 pi. What am I going to do to get there? If I subtract 2 pi, I'm still not going to be there. I need to subtract 4 pi from each of these. Everybody's okay with that? So if I do that, I'm basically subtracting, what is that gonna, 4 pi is like 8 pi over 2, so it would be negative 7 pi over 2, and then negative 5 pi over 2. And then same thing here, except when I subtract 4 pi, that's really like 16 pi over 4. Oops. Right. So those should be my answers, right? Yeah. What do you think? Good timing because we had a minute left. But that closes out chapter 6. You guys should now be able to do all